So going over this exam, the first part of the video will be going through all the questions, and I'm going to teach you how to find the correct answer. And then at the end of the video, I will show you all the answer choices just on one page or 2 pages, so you can see it all at the same time. So if we take a look at question 1, we see that we have a sulfol group right there, and we have an ethyl group. And what we have is acid and heat. And those are just conditions to take off the sulfol group. So we're just getting rid of that guy. So that would leave us with that. So it's desulfonation. Question 2, identify from the following compounds the conjugated diene. That's just remembering the definition that conjugation is just a repeating pattern of double, single bonds. When you take a look at that, you will find that we have compound C is the one that's conjugated. Which of the following compounds has the longest lambda max? The compound with the longest lambda max is the one that has the shortest HOMO-LUMO gap. And the molecule that has the shortest HOMO-LUMO gap is the molecule that has the most conjugation. So there's conjugation, conjugation. Those are isolated. But there we have 3 pi bonds all conjugated together. So that has the most conjugation, has the smallest HOMO-LUMO gap. And because it has the most conjugation and the smallest HOMO-LUMO gap, that makes it have the largest lambda max. Question 4. Identify the expected major product for the following reaction. So in order to do this one, it'd be good to do the mechanism. If we draw, so HCl, we see that it has some heat attached or is being used. So that's going to tell us that we want the thermodynamic product. And so when we add that hydrogen, we're going to add the hydrogen there so we get a tertiary allylic cation. And then the chloride is floating around. And then that's just going to, if it attacks that carbocation as is, then we are going to get a 1,2 addition. But we see that heat is being added, so we're thinking thermodynamics. So we need to draw a resonance structure. When we draw that resonance structure, we now have the carbocation right there, and this allows the chlorine to attack there to give us the product in a 1,4 addition. We'll see the hydrogen was added there, and the chlorine was added here, and that's a 1,4 relationship. Plus, look at the product right there. That is a tetrasubstituted alkene, so it's very, very stable. But one thing you need to be aware of is when this chloride attacks that carbocation, it can attack from the top face or the bottom face, giving us a mixture here. And so that's going to give us answer C. Okay, so the way I drew my product, I just drew that line. That's not correct. We would have to draw it as either a wedge or a dash, but both would be correct. Okay. So question 5, identify the products of the 1,4 addition reaction of 1,3-hexadiene. So we first need to know what hexadiene is. So we draw it like that. There's our hexadiene. And when you add the first bromine, okay, pay attention, it says Br2. It's not HBr. So we're adding 2 bromines across. it asks for the 1,4 addition. So if we add our first bromine here, okay, if we add that there, then we're going to have a carbocation or such, right? Well, let's look at it this way. It has to be a 1,4 addition, right? That's the hint. So we don't even really need to look at the mechanism for this problem. It's just looking at the answer here. That's a 1,2. That's a 1,4. 1,2, 1,2, 1,2. So the only product here that's in a 1,4 is number 3. So that's answer E. Identify the following compounds, which one is anti-aromatic. Well, this guy right here doesn't have all sp2 hybridized atoms within the ring. So this guy is non-aromatic. So that's out. The oxygen atom has 2 lone pairs, and if we count how many pi electrons there are, there's 2, 4, 6. So that's aromatic. Sulfur, same spot on the periodic table, not same spot, same group as oxygen. Same idea here, 2, 4, 6. So that's aromatic. Nitrogen atom has a lone pair, 2, 4, 6. So that's aromatic. And then boron has no lone pairs, so there's only 4 pi electrons, and so that makes that anti-aromatic. So 6 is A. Okay, if we name this compound, we see that this group right there makes it a phenol. Bromine doesn't do that, or gives it a common name. So that means that carbon that the OH is attached to gets priority number 1. So now the anilines are not an answer choice, right? So now we're down to 3 answer choices. So it's just really, do we remember the rules of the IUPAC? So do we number this way? No, you don't, because you give bromine a number 5 location. If you number this way, 1, 2, 3, you give the bromine a lower locant number. And that's the game plan. That's the rule. So the answer right here is D. Identify the major product of the Diels-Alder reaction. If we take a look at the mechanism, those pi electrons there, there. Let's see here. Yeah. When we draw that product, what are we going to get? We will definitely get a 6-membered ring. And we only used one of the pi bonds there. So there's still the second one there. And then we're going to have our substituent coming off of it like that. And does any of those match that answer? And looks like A does. Question 9. Arrange the compounds shown in order of decreasing reactivity towards electrophilic aromatic substitutions. So recall that electron donating groups make the reaction go faster because we're adding electron density to the benzene ring. And so when we take a look at these, we can identify that as an electron withdrawing group. That's an electron withdrawing group. Okay. Halogens are electron withdrawing groups. And then the amine and the methyl are electron donating groups. So with that, what we can say is between the two electron donating groups, the aniline right there has a lone pair that can resonate in. The methyl does not. So between those two, the aniline would be the most reactive because it can donate the most electron density into the benzene ring. So that's number one. So that's number one, that's number two. So now when we take a look at our answer choices here, we see that that and that line up. Okay, that matches our prediction. And so that matches our prediction, but that one does, the next one does not. So that one's out. That one's just completely out. That one's out, and that one's out. So by process of elimination, just knowing those first two, you got the right answer. Okay. But if we talk about it, we know that halogens are not the strongest electron withdrawing groups. So that makes sense. And then this positive charge withdraws the electron density the most. Okay, question 10. Which of the following represents the HOMO of the 1,3,5 hexatriene? What does hexatriene look like? Looks like this. Okay. There's 6 atoms in a conjugated system. That doesn't look very nice. Let's kind of looks like there's a Texas carbon there. There we go. So what we see is that there's 6 p orbitals. So in the MO, we're going to take a look at those 6 atomic orbitals, and then we look at it in terms of a molecular orbital. And so let's take a look at, so let me back up a little bit. How many pi electrons do we need to account for? That's what we're looking at, and there's 6 pi electrons. Okay, and so we have 3 energy levels here. Well, let's spread those out just a little bit. Okay, so we have these 6 electrons that we need to account for. So if we have the 6 pi's, or p orbitals here, I'll just draw all 6. 1, 2, 3, 4, 5, 6. In the lowest energy state, they're conjugated, and there's constructive overlap. When we jump up to another energy level, we increase the nodes by 1. So in the bottom, there's no nodes, but then in the top one, not the top one, the next one, we have to put in a node, and that just goes right in the middle. And so that means these guys are out of phase. There's a node, and then they stay, goes like that. Okay. And then the next one, we're going to need to include 2 nodes. And when we include those 2 nodes, it's going to be right here, right there, and there. So that means this guy and this guy's going to be out of phase. And then this guy's going to be out of phase like that. And then if we keep going, we're going to have the LUMO right there. So that's our LUMO, and this is our HOMO. And it asks us what does the MO look like for the HOMO. We just drew it right there. And do we see any matches to that structure right there? And it looks like that matches. It's inverted. Okay, but that doesn't matter. It's still saying the same thing. Okay, so that and that are saying the same thing. Okay, question 11. So after this right here, X, that's just a Friedel-Crafts acylation, so that has to be this compound right there. And then after Friedel-Crafts acylation, we do a Clemmensen reduction, which will get rid of that ketone. Turn into that. So answer choice C for that one. Okay, so here's the oxidation of the benzylic carbons. And so we just have to remember the rule that when you use the oxidizing agent, you can oxidize benzylic carbons if they have at least one hydrogen. So that's a benzylic carbon, that's a benzylic carbon, but only this benzylic carbon right there has a hydrogen attached. And so that's the one that's going to be oxidized into the carboxylic acid, and this guy's going to not be touched. So what is that group right there? That's just a tert-butyl. So we're trying to find answers with the tert-butyl. And so just looking for that tert-butyl, then that one's out of the picture, that one's out of the picture right there. So now it's just between B and C. And so we just now need to remember what is it? What is the benzylic carbon going to be oxidized to? And that's going to be the carboxylic acid. Okay, so that would give us that as our product. So answer choice B. So the tropylium carbocation there. This energy diagram is using more or less Frost diagrams to help figure this out. Listening to my lectures, you would know, hey, that is aromatic just by listening to lectures or reading the textbook. So if you remember that, then obviously answer choice A is off the table, and C and E. Okay, so just remembering that, we've got it down to just 2 answer choices. Okay, so when we take a look at the energy diagrams, how many pi electrons are there? When we look at it, there's 6 pi electrons. And so when we look at this number 1 energy diagram right here, how many pi electrons are we showing there? Or how many electrons there? 2, 4, 6, 8. We only need 6. There's only 6 right there. So it's energy diagram 2 is the correct answer. So that leaves us with, let's see here, 2, 4, 6. So that would leave us with what? Answer choice B. Okay. Number 14. Let's see, we're checking something here. Okay. Which of the following dienes cannot undergo Diels-Alder? Well, we need to remember that they need to be in the S-cis conformation. Okay, and when we look at the S bond, which stands for single, in the diene, we're looking at that bond, that bond, that bond, and that bond. And so this molecule 1, that is S-cis. Molecule 2 is in the trans, and that trans conformation is locked into place because it's within the ring system. This one right here is in the trans, S-trans, but there's free bond rotation around that single bond that's highlighted in red. So that can get converted into the S-cis. Okay, and then this bond right here, that's the S-trans, and that is locked into place because it's within the ring. So those guys, no go. This S-cis one is locked into place, whereas this can become S-cis. So both of those would be able to react. But what is the question asking? Which ones cannot? So I needed to cannot undergo Diels-Alder. So that means those cannot right there. And that would be the correct answer choice. So answer choice A. Predict the major product of the reaction shown below. If we do a mechanism, an incomplete mechanism here to help illustrate this, realize that your intermediate here is going to look like this. Like that, okay? And then we're starting out with a primary alkyl halide there. So we have this hydrogen atom that's right here. That's going to be used to do a hydride shift and kick off that chlorine, okay? That complex there. And that's going to give us this species right here. Like that. And that is simply the same thing as drawing it like that. Okay, our tertiary carbocation. And then the benzene ring right there, that's going to then react with that carbocation. Okay, and so our substituent has to be a tert-butyl, which is that guy right there. So 15 is going to be answer E. Okay, answer E. Let's see. What do we have here? Draw the Diels-Alder reaction. Okay, so there's the bond that we need to make sure that it is S-cis. Right now it is S-trans. So we got to get that taken care of. Like that, okay? Just like that. And then we will react that with our dienophile in the mechanism that we are so used to seeing. Okay, just like that. So that will give us a 6-membered ring. Okay, like this. Double bond there. And then we have to pay attention. Where's this electron withdrawing group going to be added with respect to this methyl group? It has to add it in the ortho or para positions, and in this particular reaction it can only add ortho. So we're going to add it there. Okay? But how does it add? Endo or exo? And so you have to show the stereochemistry as well. So like that. Remember, the outside group and the electron withdrawing group are going to be on the same side of the product. Okay, and so then you would also get the enantiomer there. Okay. So that's the product. If you've drawn it, that would work. Let's see, you could have also drawn it like this. Okay, the hydrogen's coming up, your methyl's going to be coming down, and so your carboxylic acid would also be coming down like that. So you could have had that product. Or those are the same products, it's just that's how you would have drawn it. Okay. Draw in the missing dienophile. Okay. So what I see is a 6-membered ring our diene. Okay. And remember that I said on the test that there was a typo. We have to have these double bonds right there. So when we take a look at those, let's just trace our ring here. So this ring right there, that 6-membered ring, is this piece right there. Okay. So then all we're worried about is these 2 carbons right there. So that would have to be an alkene. And then what's the relationship between these the nitriles? They're on the same side. So the stereochemistry is retained in the Stills-Alder reaction. So that's the structure that you would have to have drawn. If you drew this one, that's incorrect because we can see those are trans to one another. In the product, they're cis to one another. Now, which is the correct product between the 2? It would be this guy right here. This is our endo product. And it's endo because we're looking at the inside groups. Okay, when we look at our diene, we have a hydrogen and then that group. A hydrogen and then that group. These guys, the hydrogens are on the outside, and on the inside is the 2 carbons, which when you look at the product are right here and there. And the endo product is going to be when those carbons and the electron withdrawing groups on the dienophile are on opposite sides of one another. Okay, so that is the endo product. If we take a look at this is a retro-Diels-Alder, which means we're just going to break the 6-membered ring into the 2 pieces that it originated from. And if we do that, all we have to do then is the opposite mechanism that we did to form the original product. And so that would mean these pi electrons here would have to come back. This bond right here would have to break and go there. Then that single bond would have to go there. And when we draw what we see, we're going to have this bond, this bond, this bond, a double bond there, double bond there, there, and then we would have our carbon, our methyl group right there. Okay, so that piece that I just drew right there came from these carbons right there. And then in green, we need to account for this and that. And so if we take a look at that, then that would mean we have a double bond there and then a CHO. So our dienophile is that guy. And our diene, whoops, on our diene, I forgot that we have those carbons right there. Okay, so this carbon is that carbon. There we go. That looks better. Just like that. Okay, let's see. So problem 17, this is just naming things. Let's see here. This guy right there is toluene, phenol, anisole, aniline, benzoic acid, styrene, benzophenone, and benzaldehyde. Okay, which of the following molecules has the least amount of proton NMR signals? So we just need to we need to identify the signals. So those are the same. Those are all the same. So that would give us 2 signals. This guy would give us one there, B, B, C, and C. So that would give us 3 signals. Let's see here. A, B, C, C, D. So that's 4 signals. And that'd be A, B, C, C, D, D, and E. So that would give us 5 signals. So what do we have? This, you would say, hey, that guy has the most. And you'd say, that guy has the least. Draw the expected products for these reactions right here. One thing you need to remember is that's an electron withdrawing group. So that means that the carbon atom is going to be reduced. So then that would leave us with, that's going to be reduced, so we would get a compound like that. So this is a Birch reduction. And you know it's a Birch reduction because you have solid sodium in methanol and liquid ammonia. When we look at this one, we see that is an electron with donating group. So that means the carbon that it is directly attached to will not be reduced. So you just draw your benzene ring, your electron donated group, it will not be reduced, and then the other carbons will, to give us that product. Okay. Let's see here. And then this last one, draw the complete mechanism of the nitration of benzene. You can see that in your textbook. Right from the textbook. You'll find the answer there.